Continuing on, we're going to talk about light as a particle. So we left off with this idea that something is odd about light. When we think about waves, usually the amplitude of the wave corresponds to energy, and we've treated light as a wave so far. Yet, about 120-ish years ago, people did some experiments and found out that if you shined purple light onto a surface, it didn't matter how bright the purple light was, which would be think of for amplitude. No matter what, when the purple light hit the surface of the metal, you would have these electrons come out of the surface of the metal. If you made it brighter, you would just get more electrons, but they wouldn't come out any faster. If you had green light, you could get electrons to come out, but they all come out slowly. Again, more light just meant more electrons, but they weren't coming out faster. Red light, doesn't matter how much light you had. You never were going to get electrons to come out. And so there's something going on here. Light is not behaving like we know waves do. It's doing something different. That something different is that light behaves as a particle. So light, we think of traditionally as this continuous wave, right? When the light comes out of the light bulb, it's a continuous wave all the way into your eyeball. Instead, that light that you see is made up of individual bits of light that we call photons. Photons are still characterized by wavelength and frequency that we've talked about before. They still travel at the speed of light. They just now, we can think of, they have a start and an end. So the traditional kind of wave idea would be, the light comes out of a light bulb and then it just kind of follows this wave pattern up and down, moving through space until it hits something. But instead, a photon view is there is nothing, and then the kind of burst of energy from the light photon, and then it's gone, right? Then that's the photon. So it's like a little ball flying along, okay? And so what this is getting at is the idea of what's called quantization. So the quantization of light tells us that you can't just have this continuous beam of light. If you want more light, you need to add one photon at a time. One photon, two photons, three photons. You could count them. Okay? This is similar to the idea that matter has countable atoms. In everyday life, quantization shows up in stairs. When you are changing your height by walking up and down stairs, that is quantized. You can only change your height by units of stair height. A ramp has continuous height, right? You can be anywhere along the height of this ramp. But for the stairs, you can be right here, or you can be right here, or right here, or right here. Where you can't be is right here. You can't be in the middle of a step, right? You have to be at the height of a stair. So your change in height changes by a quantity that is called stair height, and that's what quantization means. You have to have particular amounts. So for photons, for light, you have to have a particular number of photons. So when we see something like a laser pointer, it isn't just a continuous beam of light, this wave that's super janky, coming out of the laser pointer. It is instead a stream of many photons, beep, 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 coming out one after the other. Photons are very small, and a beam of light has a ton of them in it that you wouldn't necessarily notice it, but light is made up of these individual photons, and that has some important implications. So these photons have energies. Energy of a photon is based on its frequency. So this explains what we saw earlier. When we're talking about light, the energy does not come from the wave nature of light. The energy comes from this photon nature of light. And the energy is directly related to frequency. So the energy is equal to h, which is called Planck's constant, 6.63 times 10 to the negative 34th joules times seconds. That's just a number that we can always look up. So whenever we see a lowercase h in a problem, that's Planck's constant. And then nu is the same frequency that we had talked about. So that explains the different colors that we saw. Purple has the highest frequency of visible light, so those photons have the most energy. They could cause the most change in that metal surface. If we think about electromagnetic radiation now, we can return to our spectrum. Low frequency light has photons with lower energy. So lower energy photons are less capable of causing changes to matter when they hit. We think about that purple light made electrons come out of the metal surface. Red light doesn't do that. Things with even lower frequency than red light, for example, radio waves, microwaves, low IR, those don't have the ability to really cause any harm. That's why we use them for like communications. That's why radio waves are used for communication. Wi-Fi, your cell phone, microwaves are used for like TV, all sorts of things like that where we're transmitting signals. You are constantly surrounded by these waves and they aren't causing you any harm. Just because your cell phone's not on doesn't mean those cell phone waves just go away. And so all of those are constantly around us. If we look on the other side, those high frequency waves, we have ultraviolet, we have X-rays, we have gamma rays. Those have very high frequencies, which makes them more powerful. Their photons have a lot more energy. When one of those photons collides with, say, an atom in your body, that's just a lot of energy in a single packet that's getting delivered in. So we know that as we go through the spectrum, increasing energy leads to increasing frequency leads to increasing energy. If we look at just visible light, this is still true. Red is the lowest frequency, so red light has the lowest energy photons. It goes up red, orange, yellow, green, blue, indigo, violet. The rainbow is in the order of lower energy. So if you've ever worked in, like, say, a dark room or low light conditions, this is why you use red lights. Because the red photons have low energy, so they don't stimulate your eyes, so you don't make your eyes undilate from low light conditions. Or if you ever worked in like a dark room for doing photo development, you are developing photos by having chemical reactions that are stimulated by light, so you want to use low energy photons so you don't stimulate those reactions. On the other side, blue is really high energy. This is why ambulances and like emergency vehicles have blue lights. They're really high energy photons. They are very, very noticeable at night because your eyes really respond to them because they have really, really high energy. If we keep going past blue, you get to things like ultraviolet. This is why ultraviolet light can cause you to tan or more likely burn because those photons have a lot of energy. They are higher frequency, they are higher energy. This is how you get cancer from ultraviolet light. Those high energy photons come into your cells and they can really bring a lot of energy and cause a lot of damage. And then that can lead to, messing up the cells and eventually developing into cancers. Beyond that to X-rays, these high energy photons. They have a lot of uses, say medicinally, but that's also why we protect ourselves. This person's getting dental X-rays. You want the X-rays, medicinally on your mouth. You're wearing, say, a lead bib on her chest in order to protect her, heart and lungs from getting damaged from those X-rays. So, you have some use, you point it where it's important, but you protect the rest of the body where you don't care. You're not taking X, you're not doing anything medicinally with the chest. So get that covered, protect it from those X-rays. So higher frequency photons have more energy. They can remove electrons from a surface. These photons can cause chemistry to happen. They can affect atoms that they collide with. And the higher that energy is, the higher the frequency is, the higher the energy of the photon is. You can get a little packet of energy, right? You get that packet, you deliver all that energy instantly. That's going to cause more of an effect, and you can get those electrons to pop out of the surface or, go on to go somewhere else. You start doing some, moving electrons. That's redox chemistry. Okay, let's look at an example. What's the energy of a photon of red light with a wavelength of 670 nanometers? I want the energy of a photon. What do we have? I've got the wavelength. So energy of photon does have an equation. We saw previously we had our speed of light equation. Now we have our energy of a photon equation, which again has some variables that we want to be able to parse out, some constants, some different variable symbols. So let's see what that looks like. So I want the energy of a photon. Okay? And energy of a photon is nice in that it has an explicit equation associated with it. Energy is equal to H times nu. So I want this energy of my photon. And so it just becomes a question of, do I have my other two values? Do I have a value for H and do I have a value for nu? Well, H is another constant. That's just a number that we can always look up. Whenever we see H, that's going to be 6.63 times 10 to the negative 34 joule seconds. So joules times seconds are the units on that. So then nu, we've seen previously, is frequency. So the energy of a photon is directly related to the frequency of that photon. We want to ask the question, am I given frequency? The answer is no, but I am given a wavelength. And this isn't just any wavelength. This is the wavelength that the last example had. And so you can take that wavelength and turn it into a frequency. In this case, 4.47 times 10 to the 14th hertz. And so if it was a frequency that you're given, you can just use it. We already converted from wavelength to frequency, but you could do that if it was a different value. So let's go ahead and plug them in. The energy is equal to 6.63 times 10 to the negative 34 joule seconds times 4.47 times 10 to the 14th hertz. If we see our units, it looks like we have a problem. These certainly aren't going to cancel, but we want to remember hertz is the same thing as 1/seconds. And so generally hertz is really only, it's the most common in name, but whenever we're working problems with our frequencies, we generally always need to turn it into 1/seconds. So if we have instead 6.63, 10 to the negative 34 joule second, 4.47 times 10 to the 14th 1/seconds. And the reason was now I have seconds times 1/seconds. Boom, boom. Those cancel out. And we can see that what we're going to be left with is then just going to be joules, which is good because that's an energy unit. Okay. And so I do the arithmetic. I get 2.96 times 10 to the negative 19. And joules is all I'm left with, which is an energy unit, which is good because that's what we wanted. So one of the things we can see right away is that the energy of a photon of red light is pretty small. You know, when we were talking about chemical reactions and heating things was, heating things was joules, chemical reactions were kilojoules. So one photon of light, not a lot of energy, but we certainly can compute what it is. So one thing this result tells us is that photons of light are extremely small. There's not a lot of energy in an individual photon. So one of the things about that is that this is why we don't really necessarily notice that light is quantized, right? Light is quantized, we have to have one photon at a time. But, each photon is so small that you wouldn't notice the difference between a beam of light that had one fewer photon, just because they are so small. It's a very small difference. So practically we don't notice it. But this low energy shouldn't be confused with the fact that it's not important, because you're calculating the energy of a single photon. So the 2.98, that is per one photon. If we turn that to say a mole of photons, now all of a sudden we're looking at 180 kilojoules per mole of photons. The energies that we dealt with chemical reactions, which were also on the order of hundreds of kilojoules, were hundreds of kilojoules per mole. So red light is just on the border of maybe causing some low energy chemical reactions, but not a lot, right? As you get up though into higher light, say you get to that purple light, you push further, ultraviolet light, those energies are going to go up, and now you're on the order of more than is the endothermic cost of some of these chemical reactions. And these high frequency lights can really cause a lot of chemistry to happen. Say this really endothermic reaction that wouldn't want to happen otherwise. All of a sudden, you got some photons. You can make it happen.